everybody, this is Jesse, and I'm going to present today's paper, which is PStore, Elastic Database System with Predictive Provisioning. This is by some people from both MIT and a Brazilian retailer. And the first author, Dr. Rebecca Taft, is generously here with us to join our discussion. So the authors collaborated with, one sec, I need to rescue my mouse. Okay. The authors collaborated with this Brazilian online retailer called BTW. So that means that they have real data from a real large retail system. B2W is called the Amazon of Brazil. And since life is completely absurd, they don't mean the Amazon River in Brazil. What they mean is the online retailer of Brazil. B2W's workload looks like this over the course of a few days. It's very spiky, and the peaks are about 10 times higher than the troughs. And it's also extremely cyclical. Every day has its kind of rhythm. It probably also has weekly cycles, which this system could capture, and yearly cycles, which it doesn't, but probably could. It's got this really strong daily cycle just because most of its users are in Brazil and most Brazilians are all in the same time zone. So the status quo way to deal with this kind of spiky workload would be reactive scaling. And that would mean that you would start scaling up during the load spike. But that requires a trade-off where you have to pay for lots of useless headrooms at all times just to avoid suffering poor performance while scaling up during the spike. So in reactive systems, you maintain some amount of headroom, which is a waste of money. And then when the load spike arrives, you detect that because the spike is eating into your headroom. And then the system responds by scaling up. But scaling up also is a process that contributes to the load. So you need enough headroom to deal with that as well. We can work to make systems scale up as quickly and efficiently as possible to minimize the amount of headroom that you need, but there's always going to be this trade-off between excessive headroom on one side or sometimes violating your SLAs on the other side. But if we notice that these are cyclic workloads, we can take advantage of it because they're fairly predictable. So that's what this paper is about. It's about predictive scaling. The system, because it knows when the load spike is probably coming, it starts scaling up before a load spike, starts scaling just early enough to be ready when the spike arrives. Therefore, it avoids overload during the spike and maintains its performance, but it doesn't pay for any more headroom than it really needs. So some more details about the actual implementation of PStore. It's based on HStore, which is a research prototype, an in-memory partitioned database with a really interesting concurrency model. That was commercialized into VoltDB, which is equally interesting. They are main memory databases, they're sharded. And in this paper, it says that HStore is not replicated just for simplicity. I assume that in a real deployment, you would need some sort of availability solution for that, but that's not what this paper is about. So the problem is this, that you've got this spiky demand curve, and you want to keep just enough capacity at all times to meet demand with a tiny bit of headroom, but no more than is absolutely necessary. Just obvious background, we're assuming that you're using a cloud provider to rent capacity from. So whenever you reduce capacity, you save money. You can't continuously vary capacity like it's shown here. You have to remove whole machines at a time. So capacity is actually more of a step function. And even this isn't accurate because when you add a server, it doesn't instantly increase your capacity. You have to rebalance the data. So According to equations in this paper, capacity rises on a sort of a curve until it meets the full potential capacity of the server that you just added. So you have to keep all of this in mind when you're calculating how much lead time you need before the spike in order to scale out and be ready by the time it arrives. So how do you actually do that? How do you forecast demand? So the authors use something called sparse periodic autoregression. I have not read the linked paper, so this is a fuzzy understanding of mine. They can base their prediction of the future based on the previous week's history. It could be any time span. And then they look at the last 30 minutes and compare that to sort of past averages for that time of day, or more generally, like that portion of each of the periodic curves. So I think that if this is a Monday, last Monday might be more important for calculating this offset than last Tuesday was. I think that would make sense. So from that, you get an offset that tells you kind of that might account for you know, a growing customer base or some temporary increase or decrease in load. You combine the periodic prediction with the offset and use that to forecast the next 60 minutes. You want to look a fair bit ahead, because if there's a giant load spike coming in the future, you might need to prepare now, even if the next 5 minutes are going to be pretty stable. So the chart that the authors show suggests that SPAR is extremely accurate for the B2W workload, generally with a relative error around 10%. This is already a huge win. I'm sure there are other papers out here that talk about predicting load spikes based on cyclic history, but I haven't read any of those before. So I think that this is already just a really clever way to deal with this kind of problem. So given a prediction for the future, now we need to model how quickly the system can scale up so we know how far ahead of time to start. And system modeling uses 3 parameters: Q hat, Q, and D. For a single server, we need to know its max throughput Q hat, and they do that just with an experiment. They subject it to more and more load until it starts to get slower. And then they set a target throughput, which leaves some headroom, and they call this Q. But they actually want even more slack than this, just to ensure that they don't break SLAs. So they actually set Q hat at 80% to the max throughput and the target throughput at 65%. I think that this might account for things like the load is not perfectly evenly distributed across servers, or your prediction might be off by a certain percent. So that's the first 2 parameters. And then the last one, D. D is the time it takes to transfer all the data from one server to another server. And they also determine this experimentally. They don't just run a transfer as fast as possible. They experiment to see how fast the transfer can go without affecting user operations. And then they set D to that speed. So with those 3 parameters determined, we know how long rebalancing is going to take. And this starts to tell us how soon we can start scaling out before the spike arrives. So the next problem that we've got is to actually figure out how to get from here to there as cheaply as possible. So this chart is from the paper, and you've got a point in time now, you've got a week of history, and you also want to figure out, well, you've got a forecast for the next hour, so you need to come up with a plan to get through the next hour with just enough capacity. And the actual prediction only needs to be used for 1 or 2 moves, but for the reasons I said before, you do create a plan that goes much farther into the future. So how do we actually come up with this plan? And here I've got kind of a bad visualization. This is pretty inaccurate. I wish I'd had time to correct this. So I'm gonna kind of tell you what I think is wrong about this idea. So, okay, so the algorithm has a matrix where one dimension is the number of time slots into the future that we need to predict. So these could be like minutes or whatever. And also a number of machines is on the vertical here. And it starts all the way on the lower right. It wants to find an endpoint to shoot for, and it wants to find the endpoint with the minimum number of machines because that will be cheaper. So we start here. And I'm kind of imagining it as if the forecast was actually superimposed on this matrix. That's the blue line. So the next step of the algorithm is to calculate the cost from every previous time slot cell to that final cell and find the cheapest way to get to that cell from the previous one. Now, in this case, none of these paths is, quote, feasible because none of them has enough servers to actually meet the load. They're going to violate the SLA. So we say that this costs infinity. We don't want to take this path. The same calculation applies to all of the slots until we get to this one, where we actually have enough servers to meet demand. So now the algorithm recurses. It says, this is a good finishing spot for me. It's feasible. What is the cheapest way to get from the previous slot to this slot? This one's infinite because it doesn't have enough servers. So we go back here to the next slot in time. And so on, kind of backtracking and eliminating unfeasible paths that don't have enough servers until we get back here where we have our starting point. Then we need to calculate a cost from the beginning point through each transition up to the goal state. And this is more complicated than I'm showing. What I'm about to show you is wrong, but like imagine that you just kind of totaled up the number of servers you had in each time slot. And since you're paying Amazon for those servers as you go, you would just total those up as you go from left to right. So that's one feasible path. Is it the cheapest one? Should we take it? We can compare it to all of the other feasible paths in a kind of depth first search. The costs are memoized as we go. They're stored in this matrix, so we never recalculate the same transitions cost. We can see here that 31 is worse than 28, so we'll choose the path that goes through 28, sum up the cost, and then this is our solution. Please read the paper. This isn't really accurate. Given this path that we've found, we also have to consider this other detail that effective capacity kind of gradually reaches the potential capacity, because every time we add a server, we have to wait for data to be rebalanced before the new server can really pull its weight. But you stick that all together and you get kind of a cycle like this, where you've got your system model, which is static. You determined it in one experiment. You've also got your forecast, which you update every few minutes as you get new data. And you stick those two things into the Pathfinder, and that tells you what action to take. You take the action, you continue monitoring. That produces more data, and that gives you an updated forecast, which you then plug into the Pathfinder again to determine the next step. So you're always planning for the future, and you're always a step ahead of the impending load spikes. So the paper makes a few assumptions. The whole system is going to work if the following are true: that the workload mix and data size are not quickly changing. I think this means that your your forecasts are accurate and you don't have to keep recalculating your Q and D. That they're also distributed evenly across the partitions. So if you add a partition, then that will scale up the system's capacity linearly. And also that the workload has few distributed transactions, again, so that you can just add more servers and get more throughput. Their evaluation, they've got a couple of charts. This is the one that really interested me. We've got a reactive system at the top, which starts scaling up as the load spike is already happening, and then the predictive system on the bottom. And you've got the pink line, which shows how many servers they have, which closely tracks the amount of load that they have. And then below that, you've got the latency graph, which has a lot of spikes, at least in the top graph, because as the system gets overloaded, it experiences latency spikes, probably both from the underlying load as well as the load incurred by the scaling out process. Whereas the one below has no spikes. So mission accomplished, because it always scales up ahead of time. It never violates its SLA. I am curious why the system seems to over provision a lot sometimes. I wonder if that's due to inaccuracy in the prediction or what. But like sometimes it really seems to have almost twice as much capacity as it needs. But anyway, this is a small price to pay for always making your customers happy. My evaluation of the paper is that the kind of starting insight that since workloads are often cyclic, they are predictable, that's just an amazing place to start. And I haven't seen that often enough in papers. And also calculating how much time you need ahead to start scaling is also brilliant. I think that implementations, they don't need to use SPAR and they don't need to use this pathfinding algorithm in particular. For me, the overall system concept was more valuable for me than the details. So when I'm working on systems like this, I might or might not be copying the specific implementation ideas, just having this orientation towards customers with cyclic workloads is just this real shift in thinking. I think that to really deploy this system to the real world, all those evaluations, by the way, were simulating a B2W workload as if it were running on pStore, but pStore wasn't actually deployed to the retailer. I think that if you were doing this in the real world, you would want to automate the discovery of the model parameters and keep them updated. You might release a software patch that makes your system faster, and so the same server can deal with more load, or usage patterns might shift. So you would want to keep these updated over time as well. And I think that skewed workloads are a fact of life for a lot of real world systems. And so you would need to figure out some way to deal with that. I'm not sure how. Further reading, this is part of this whole family of papers. There's a great paper on HStore and on its commercialized version, VoltDB. There's a paper from the same lab about Clay, which is great, about if you do have a lot of distributed transactions, how do you keep data close together so that you minimize them? Another paper with Dr. Taft as the lead author, eStore, is a reactive system that uses partitioning in 2 tiers to identify hotkeys and move them to quickly alleviate hotspots. And Dr. Taft's thesis, which covers both eStore and pStore, it's got the same stuff, but in more detail, and it's a really good read. So that is my presentation, and let's open it up for discussion. Oh, and I'll share these slides afterwards, so you don't need to copy down these URLs right now.